Hello, this is Dan Allford.
Howdy, this is Abbey Fossati.
We're back with another ARC Challenge Coin Challenge. If you recall, a few weeks ago, we did alloy loss across the ARC. We used several different welding processes, and we've observed how much the chemistry changed between the wire and the final weld. What were our results?
We saw pretty consistent trends in manganese loss across the ARC.
And that made sense in retrospect because manganese is used as a deoxidizer, so there's more manganese in the wire than there is in the weld deposit. But we observed something else when we looked at the data closely. We saw an alloy gain, so we went back to the lab and conducted a second set of tests.
We ran 3 different new tests this time. We did a short circuit transfer using C25, which is 75% argon, 25% carbon dioxide, and another short circuit process on a trimix, which was 90% helium, 7.5% argon, and then 2.5% carbon dioxide. The third with the spray arc process using 98% argon, 2% oxygen.
And what was the wire?
316L on 316L plate.
And what we observed was an alloy pickup. And in one case, at least, we were actually driving the alloy up above the limits of this specific material. I found it interesting. So for an ARC Challenge Coin Challenge, I want you to identify what alloy increased to a point that it exceeded expectations. Hello, this is Dan Allford.
Howdy, this is Abbey Fossati.
We're back with the ARC Challenge Coin Challenge answer to last week's question. What we asked you was, what alloy actually is picked up and increased when you weld through the ARC? And the answer is?
Carbon.
And where do you think that came from?
The different shielding gases. So just as a reminder, we ran on 316L wire and then 316L plate with 3 different gases. So it was a trimix, 2 oxygen, and then 25% carbon dioxide. So it makes sense that in fact the test that we ended up picking up the most carbon on was the C25.
And these are 2 different welding processes.
Yep. 2 were short circuit and then 1 was a spray arc.
So I found this interesting because we actually exceeded the specified carbon limits on 316, which is supposed to be down at 0.03.
Yep. And then the wire that we started out with, just to make sure, was 0.01. And this is in weight percent of carbon. And then it got up to almost 0.06 weight percent carbon for the C25 mix.
And this seems like a trivial percentage, and it is. But what you have to consider is this a weight percent. With carbon being as light as it is, it's a significant addition of carbon to the deposit. And more importantly is the metallurgical effect that you get from carbon on stainless steel.
Mm-hmm. Whenever you exceed that low carbon limit, you no longer have low carbon material and you lose a lot of the mechanical properties that are associated with that, including corrosion resistance. And it also affects the structure that you might get in your different welds, how that carbon is tied up, what inclusions might be in there as a result.
Typically, if you have too much carbon in a 316 deposit, you'll tie up the chrome as chrome carbide. And the whole point of the chromium in stainless steel is to create a chromium oxide layer to prevent corrosion. So if it's tied up as chrome carbide, you get corrosion. Well, typically at ARC Specialties, whenever we answer a question, we end up with another question. So since most of you guys out there that are going to be welding 316 stainless are probably going to weld it with short spark, we went back to the lab again and focused on short-circuiting transfer welding of 316 stainless. What were your results?
We actually saw the same trends as we did in the previous mix. Out of those 3 gases that we used for short circuit, the C25 had the highest amount of carbon, the trimix had about a medium amount, and then it was the original gas that we've used actually in the first set of tests, 2% carbon dioxide, that had the lowest amount of carbon.
Predictably, it's directly related to the amount of carbon dioxide in the shielding gas. And in only one case did you exceed specified limits for carbon, and that's C25 with short-circuiting transfer. Mm-hmm. So that's the lesson for today. If you're going to be welding short-circuiting transfer, gas metal arc welding of 316L stainless, we're going to caution you not to use C25 gas, and certainly don't use CO2. So we're going to recommend either a C2, 2% carbon dioxide, or the trimix if you can afford the helium.
Yeah.
Thanks for everyone that's participated in this ARC Challenge Coin Challenge. I hope it was useful for you. We'll be mailing out that challenge coin to our winner. If you have any comments or suggestions or experiences, please post them below.